Hello, data voyagers. I am Igor Alcantara, and I'm here to talk once more about data science, statistics, those topics that I love and I hope you like. And I will talk today about actually two concepts: correlation, which a lot of people are familiar with, and mutual information. If you already know these topics, please continue watching this video. You might learn something new. So let's get started. Let me share my screen. So this is um, just a demo application, and I'm using data from this is a very common, popular data set for data science study, and I use in my classes like many times in the past. And basically, it's data from for vehicles in the 1980s. I think this is 1985, if I'm not mistaken. So we have a sample of 193 vehicles sold in the United States with an average price around $13,000. Yeah, I missed those prices. But anyway, we're trying to predict or we're trying to understand what drives the price of vehicles. In this case, back in time, but we can also relate to currently if we have a like updated data set. So, a few things comes to mind. Like, is it the engine size, the biggest engine, more powerful the car, possibly more expensive? So let's plot it, those two variables, the engine size in X, price in Y. We usually, that's a industry practice in statistics. Whatever you're trying to analyze, which we call our dependent variable, you put on y axis, and what you trying to input as a variable of study, we call it the independent variable, you put in x. So if we're analyzing what impacts price, then price always go on y, and that's the way we write it this so people will understand it's the syntax here. But anyway, plotting, we see that there's very good linear relationship between those two variables. How about horsepower? That's another measure of how fast or powerful the car is, and we know more powerful, faster cars, they're usually more expensive. So let's see. Also, pretty good linear relationship, not as good as the engine size, at least visually. So these dashed line here, it's our regression, linear regression line. So the closer the dots are to the line, the more linear is the relationship. Then we have the how much fuel it consumes, like the highway mileage per gallon. And then you see there's a reverse look at now the line is going down. So the highest the mileage per gallon, the lowest the price. So then more economic cars have a better price, which is interesting because it looks like it's the opposite of what we find because like those like muscle cars, they're usually not very economic. But anyway, and the curb weight, right? What is the weight of the car with the fuel, oil, and everything? Also, pretty good relationship. The heavier the car, then the more expensive the car is, and we have a interesting linear relationship. And I color based on the fuel type just to see that some of these like the engine size, horsepower. You see the diesel are a little bit more distant to the line, so they're a little bit more or less predictable. But also not a lot of cars that runs on diesel, at least on the 80s. And same here. The only exception is the curb weight, which all of the points kind of a very similar behavior, regardless the fuel type. And we have a few outliers here and there, but pretty good. Now, how do we measure how good is the relationship between these two variables? Well, the basic way is a correlation. Correlation basically tell us how much a variance in X impacts the variance in price. Let's see, if I double the engine size, how much would that impact the price? That's a measure in a nutshell of correlation. So I had some KPIs here ready to go. So we make this video not too long. Let's calculate some of these correlation. Let's start with this first one here, the correlation between engine size and price. So let me click edit sheet. Let me go to this KPI. I don't have an expression here. So the function for that in Qlik is correl with two R's. And then you basically provide what are the variables. So let's say I want to do price and it's engine size. There you go. Close parenthesis, click apply, and we have a value of 0.89. What that means is, well, correlation score, it's a score. So it varies from -1 to +1. So the farther you are from 0, the highest the correlation. So it doesn't matter for the size of the correlation if it is positive or negative. The positive or negative means something else. So the closest to 1 or -1, in other words, the distance from 0 means higher correlation. So some people like to translate this into percentage because it's easier to read. So it's like 89%. So we can explain 89% of the variance in price by the variance in engine size. Does it mean that a car with a larger engine will correspond necessarily to a more expensive car? No, correlation is not causation, because there might be other factors. Maybe it's not the engine size the actual cause, it's something else. But in order to get this something else, you need to increase the engine size as a side effect. We don't know until we investigate it, but this is not the goal of this video. All right, so 89 is pretty good because the max is 1. So we're close to 1. Now, I have these other correlations here. It's the same formula. I have them commented so we don't spend too much time. Again, it's correl, the name of the function. If you want to learn more about any function in Qlik, you simply click the help mode here, and then this becomes a link. You click on it, and then it will open the Qlik help. And then you turn off if you want to continue interacting. And then you put the two variables. That's it. Very simple, very simple. All right. So look at this. We do have 89 correlation here, 81 correlation here, -72 here, which makes sense. What negative means is if you increase one value, you're likely to decrease the other value. They are inversed. So if you increase the mileage per gallon in the highway, then you decrease the price. And then we have curb weight as well. So the highest one here is the engine size, the highest correlation, and the second highest is the curb weight. All right, because they are in the 80s. This is also in the 80s, but it's low 80s. All right, pretty good. Now, this has limited capacity. Correlation is very good. It gives you some insight, so then you can later investigate. However, there's a few a few limitations with correlation. One of them is it only works for obvious reasons with numeric values, and it only calculates a linear relationship between two variables. Sometimes two variables, they do not have a linear relationship. They have a more complex relationship. It's not linear. Linear, when I say linear, is like the first degree functional equation, like a line. So let's look at this, for example. I'm plotting, this is a distribution plot. I'm plotting the price against the fuel type. So we see the gasoline cars, they tend to have the most expensive cars. So the most expensive diesel car is a little bit above the median of the gasoline. What about the body style? Then, well, we have like hatchback wagons. They don't get like crazy expensive, where every other type gets. And then we have also, of course, the type of the car, the brand of the car. the maker like Mercedes, BMW, Porsche, like the three Germans are more expensive overall, and then Jaguar and Audi, etc. And then Chevrolet, like the cheapest, and all the prices are pretty similar based on this sample. Again, this is not today's data. Pretty good. If I want to calculate the correlation using these, I can't. If you want to calculate a correlation with variables that are not, they don't have a linear relationship, they might show a very small correlation, but they actually one variable impacts the value of the other, but the correlation will tell me otherwise. So analyzing the correlation alone only tells you part of the story. To get more to the story, we need more statistical tools. And one of my favorite, because it's very simple to implement, is mutual information. What is mutual information? And if I was not wearing this shirt, I could show you my tattoo that I have, an equation for the channel entropy equation. So basically, mutual information is related to a concept called entropy. Entropy in data or in statistics is the measure of how much uncertainty you have in the data, how much of the data you don't know. That's entropy. So basically, mutual information is a measure of how much information. Let's say I want to calculate mutual information between price and engine size. So how much information about price I can get if I only have the engine size. In other words, how much entropy can I reduce in price if I know the engine size? That's mutual information. Um, the formula is also very simple to implement. However, there is one extra parameter than if you compare to correlation. So let's get to work. Let's calculate the mutual information here. And mutual information is a score from 0 to 1, by the way. We don't have negative. We don't have negative because knowing something doesn't decrease your knowledge of something else. It will either not affect or increase. That's why we don't have negative. So let's come up here, and the function is mutual info. And I have three parameters. So the first two is just like correlation. What are the variables? So let's say I want to do price and I want to do engine size. Very good. However, I'm missing a parameter. You see, too few parameters. That's my error. The third parameter, and I'll put, you can put a number, but I find it's easier if you just put the string. It's what type of information is these two variables. And I have basically two options. They can be continuous or they can be discrete. So let's take a look at this data. So if I apply here, edit, and I scroll down, I have a table here. So if you find price, you see the price is a number. If you find the engine size, which is somewhere down here, the engine size, you will see, where is, come on, you see the engine size is also a number. Engine size is, believe me, oh, there we go, engine size. It's a number. So, and for mutual information, I can use two types of data, continuous or discrete. So what is the difference? How do I know? So basically, continuous is anything that is a number. Anything that you can sum or average is a continuous variable. So price and engine size, they are both continuous. So I'll put CC, continuous, continuous. Discrete is everything you have to count. You cannot sum. And we'll get to that. So there we go, 92. So I get 92% of price information by being provided with engine size. How about the other ones? Then I have the 91. I have here 91 again, and here 92. So look at this. regardless if the correlation is positive or negative, the mutual information will be positive. They're all high because I cherry pick the highest correlation and mutual information. And what this tells me is, well, by only having the engine size, I can get 92% information about price. This is like a rough simplification of mutual information. So if you're a statistician, don't hate me. I'm just trying to fit this explanation in a short video. Now, you know what is cool about this mutual information? You can use it for data that is not numeric. So let's do a mutual information between price and, say, how about the body style? So let me copy this here. Let me place, I don't know, like this here. And this will be the mutual information between price and body style. Let's do it. So again, is mutual info and two variables, price. Now is body style. Now, how is that possible to do with body style? Since body style is a text, it's not a number. Well, my third parameter, I will inform that price is continuous, but body style is discrete. So the methodology is different. Instead of summing, average, whatever it has to be done with the variable, it will count the frequency. And then like what is the price for each body style, in other words. So that's how it will do. So if I put this, by the way, if I mistakenly put CC, I put body style as continuous, will tell me a mutual information of 0 because this is wrong. So I need to correctly inform this is a discrete. So then it calculates me 38. Not very good. Not very good. Okay. So this is basically correlation, mutual information. I hope you like it. I hope you start using, and share this video if you like. Subscribe to our channel. Turn on notifications so you'll be notified when we publish new content, and share this to all your friends in LinkedIn, all social media. And leave in the comments use cases where you want to use this or where you used this in the past, and if you have any questions. All right. I hope you enjoyed this. See you next time, and keeping traveling, keeping with data, keeping exploring. Goodbye.